Hello and welcome back. We'll now have a short introduction to causality, or more colloquially, how to find out why something is happening. The high-level learning outcomes are here that we want to understand on a very high level what causal inference is all about, what to watch out for when using data to make statements, and using simple interaction between variables. So, first question is, why do we care about causality at all? For example, we can consider medicine. The drugs that we develop should do specifically what they're designed to do, and we want to test that an outcome is really due to this medicine. For example, if we develop a new heart medicine, we want to make sure that first of all this medicine actually does target the heart and that it provides a measurable impact on the patients. In science and engineering, we often come across a sentence like, the reason for the observed behavior X is due to Y, but how can we actually quantify such a statement? Machine learning is all the rage these days, but machine learning also solves all the problems, or does it now? Like, we have all the data, be it raw data like text, images or tabular data, put it into machine learning or AI, and out comes our prediction, like a classification, regression, or whatever it is we need the machine learning algorithm to do. So why do we care about causality? First of all of these assumes that we learn from data. So both the variables in red and blue show the same behavior over long periods of time. And this is, for example, what machine learning would do. It would learn such a relationship if we give it the black variable, for example, together with some others maybe, and we wanted to learn the red, right? It could exploit those correlations. Or imagine that we have these kind of data. We could use machine learning or linear regression, and we would end up with the fitted line to the right, assuming that we have this sort of scatter plot between variables x and y, and we assume that there's some sort of linear relationship between them. However, all of these examples I've just shown you are all wrong. But machine learning has no way of discovering why that is. Machine learning learns from the data, but it doesn't take into account the data generating process, i.e. how these data came about. So variables are highly correlated, but if we now add the labels to the data and say the blue ones are space launches and the red ones are sociology doctorates, we know from our everyday experience that those two variables may have a correlation, even a very high correlation in this case, but it's completely spurious because there is no apparent reason why those two variables should be correlated. And also here we can now add the axis labels. We have exercise and cholesterol. Of course, it's a constructed example, but the general trend shows it's the same. So the more we increase our level of exercise, the higher our cholesterol rises. That sounds tempting to avoid exercise at all costs, but it's somehow not what we expect, and it's also not the same as expected from all the health advice that tell us do some more exercise is good for you. Again, machine learning has no way of knowing this. Let's step back a step and talk about correlation. Mostly we talk about Pearson correlation, which is a linear correlation and describes how two variables x and y covary, and you can see the illustration here on the right. On the top row, this is what we expect. A correlation of 0 is sort of a blob of scattered data, and a correlation of 1 or minus 1 is a straight line where the variables behave the same or anti the same, shall we say, and everything in between is sort of a scattered version of that. In the next line, we already see that this starts to break apart a little bit because all of these are straight lines with either 1 or minus 1, but clearly they're different, and the Pearson correlation coefficient has no way of measuring this. But it gets worse. The data in the next row are clearly correlated because of their complex behavior and shape, but the Pearson correlation coefficient doesn't capture this at all. So the Pearson correlation coefficient is quite nice to describe linear and simple correlations, but it falls apart for more complex setups. Why do we care then about correlation versus causation? Take a simple example, an air pressure sensor and the rain. And we know that by measuring the air pressure, this allows us to predict to some extent if it's going to rain or not. So air pressure and rain are correlated. However, if we force the needle on our measuring instrument, this will not cause the weather to change. So there is no causal dependency in this direction. What does machine learning do? Essentially, it takes all the correlated variables that we have, even with higher order correlations, learns from those and makes our prediction. And now we can understand why this may work in some setups, but can go horribly wrong in others. So our first lessons learned are correlation does not imply causation. The correlation may be spurious or random, for example like space launches and sociology doctorates, and the fact that variables are correlated and this correlation may or may not make sense, but the correlation may seem wrong, like the cholesterol and exercise, where we know cholesterol and exercise are correlated, but the correlation we've seen in the simple example is wrong. So there must be something else going on, and we need to understand what this something is. So, shall we say, purely data-driven methods do not work, of course, with a caveat, right? But if we ignore the data-generating process, the data do not tell us everything, and we are prone to making severe mistakes. This is even leading to an anti-pattern, right? There is often the case that many people generate many variables, or descriptors as they're called in some setups, hundreds or more variables, and add all of these to the machine learning pipeline, and maybe use some automated feature selection method to keep only the good variables. But the more variables we create, the more likely we will pick up spurious correlations, even if all of the variables themselves make sense. Think cholesterol and exercise. So even if we understand the variables, just by chance, whatever, some variables will survive the selection process even if this is not right. So this is a really dangerous thing to do. How do we establish causality? It goes all back to the historic example of R.A. Fisher, who started to think about which fertilizer is best for a specific field or type of crops. So he started to devise experiments. In year 1, he used fertilizer 1. In year 2, he used fertilizer 2. Fair enough, but each year we have a different kind of weather. You could say, okay, do that in 1 year, and on the left-hand side we use fertilizer 1, on the right-hand side we use fertilizer 2, but maybe the field is slightly different, or like the drainage could be different. Or then we could say, okay, then the outer part we have fertilizer 1, and the inner part we have fertilizer 2, but maybe the soil is locally different, and so on and so forth. So we could try to devise this strategy further and further and further, and it's called the Latin square approach, and we can see that whatever scheme we come up with, there's always a reason why it might not work. We can always think of one more, but it's called confounder. So how do we establish a causal relationship? A causal relationship, and we follow the definition of Julia Pearl here, is a variable x is a cause of a variable y if y in any way relies on x for its value. A bit more informally, x is a cause of y if y listens to x and decides its value in response to what it hears. Let's explore this a bit. First of all, what is a confounder? We've already come across in this Latin square example from Fisher on the field what this could be about. And a confounder is a variable that introduces a spurious relationship that are, for example, otherwise unrelated, or introduce a different way of relation. A nice example is shoe size and reading ability in school children. So imagine you would go to a school and take a survey and take many details of all those children there, like their age, their shoe size, their reading ability, their weight, and so on. The data will now show a correlation between shoe size and reading ability. This is what you will find, and if you were to use machine learning naively, you would give all of these records to a machine learning model and predict their reading ability. Or something else, and it would learn that there's a correlation between shoe size and reading ability. But of course that doesn't make any sense whatsoever. But older children tend to have on average larger shoes, and they also, because they had more years of education, can read better. So age is here a confounder, because age affects both the reading ability and the shoe size, and of course also the weight. but it's not directly related. And this is also what happened in our cholesterol exercise. Age is a confounder here as well, because as we age, our cholesterol level on average generally rises. So in each age group, exercise is good for us, and we can see that by moving from the scatter plot we have seen earlier to one where we look at different age groups and then do the linear fit in each of these age groups, and then we find that the conclusion is completely reversed. Exercise is now good for us. So when we want to establish causality, we all either need to make sure that all of these bad influences are removed by design, even if we don't know them, and this leads us to randomized controlled trials, or we can use a causal framework to model all the relevant influences and control for them, as it's called. So that means that we remove their influence from the result. So what is a randomized controlled trial? It's essentially an extension of this Latin square approach. We divide the field in many patches, and instead of choosing now which fertilizer goes where or which group gets the medicine and doesn't, we assign the fertilizer randomly. This is in medicine the gold standard, because we sort of get random volunteers for a medical study, and then we divide all of these volunteers randomly in two groups, medicine and placebo, so we have no influence from a human part of who gets chosen for which group. One group gets the medicine, one group gets the placebo, and then we compare those groups. And the only difference between them, because everything else is random, is whether that person in that group receives the medicine or the placebo. And if those groups are then homogeneous, we can say, okay, any observed effect between those two groups must be due to the medicine, because that's the only thing that changes between those two groups. Of course, as you can already imagine, it's not quite so easy, because volunteers are never completely random. We can't just grab people off the street, right? For example, for children, you have extra hurdles. If you have pre-existing conditions, you need to take those into account. If you have a very high age or whatever, right? So it's not that you have volunteers that are really representative of the society at large. Also, patients, for example, with a terminal illness are more likely to join a high-risk study because, well, let's say they have very little to lose and they can only benefit, even if there are severe side effects of a new drug, than people who are completely healthy and, for example, go into a control group. Also, trials may be unethical. Like one example of a causal study was like, does smoking cause cancer? But we cannot just take thousands of teenagers, say age plus, make them smoke packages of cigarettes for decades, and then 20 years or 30 years later ask them if they had developed cancer, right? So this would not work. So we need some model framework to describe causality, and there are several out there. One is called potential outcomes, developed by Rubens et al., and we'll focus on here on the do calculus by Judea Pearl. This has a number of building blocks, and we start to go through them. And the key idea of this framework is that we can use directed acyclic graphs, or DAGs. So these graphs model relationships between variables, and we can express this as a graph. What is a graph? A graph consists of nodes or vertices, and they describe essentially our variables, and edges. These are the connections between our nodes, our variables. We can have two types of graph. We can have a directed graph where we use arrows pointing from x to y, and here the direction of the arrow is indicating our causal relationship. And we can of course have undirected ones, but we use now directed graphs. And what's the acyclic part of this? Acyclic means we can't go round in circles. So when we move throughout the graph, we don't end up at our starting point. So this is the basic building block on how to build a causal model in the do calculus framework by Judea Pearl. Let's take a very simple example. We have one variable x that is a cause of y. So we have two nodes, the red circles, x and y. Those are connected by an edge. We have a directed edge from x to y. That means x is a course for y is not a course for x, and both x and y are correlated. Now when we start more complex graphs, we need some more elements beyond the very simple one we've just seen. One of them is the confounder that we've already encountered with the school children, and this is essentially a fork in our graph where the graph splits into two directions. It's also called a common course. We've already seen that with the school children where age was a course for shoe size and reading ability, because if children are older, they tend to have larger shoes and can read better than younger children. The same happens also with smoking. Smoking is a cause for lung cancer, but it also causes yellow fingers. So there's a correlation between all of them, but painting your finger yellow will not develop lung cancer. What we've seen in the confounder in the school children example already is that unrelated variables like reading ability and shoe size become correlated if there's a common cause to both of them. How do we deal with that? We can control for the confounder. Once we know that, for example, age is a confounder, we can analyze the data in stratified examples for x. That means we look at different portions of values of this confounder, and this is what we've done for the cholesterol exercise. Remember, there for each age group, right, and this is our control for confounder, we look at different age brackets and then the correlation reversed. Another one is the chain, this sort of one element after the next. This is called a mediator. Take a simple example like a fire detector. A fire detector doesn't actually detect fire, it's usually sensitive to smoke. So you have fire produces smoke, fog triggers the fire alarm. So the fire alarm is not triggered by the fire directly, but it's mediated by the effect of smoke. You can test these fire alarms by having artificial smoke, so there is no fire, but they still work. We can also have sort of the opposite. This is a collider if we have multiple causes. Remember from the confounder we had a common cause, now we have multiple causes or common effect. Take the example of a celebrity in Hollywood. We could say that a person becomes a celebrity either because they're very talented or because they're very beautiful, or of course both, right? But talent and beauty are unrelated in the general population. But if we only look at celebrities, these now become correlated, because if they're not a celebrity due to their talent, then they are probably a celebrity because of their beauty. So that means that also those variables that are unrelated now become correlated if we look at specific values. And it's like a bit of the opposite what we've encountered before, because here the caveat is if you control for colliders, this makes them correlated. Remember in the previous example we looked at the cholesterol exercise and we looked at different age groups and saw the correlation, right? But here we look at, for the celebrity, we look at specific people corresponding to the age group, and that part of looking at specific aspects of our collider makes them correlated. Now that we can build our graph from these elements, we can follow paths across them. A path in a causal graph is any route between any two nodes in the graph connected by the arrows, and some paths follow the direction of the arrows, whereas other paths do not. And this is an important distinction to make. And the paths do not necessarily need to follow the direction of the arrows. And any variables that are connected by a path that is not blocked are correlated. And this is what it makes so difficult to establish causality in many aspects. If you have many variables and you have many paths between them, so variables influencing each others, then these variables all become correlated if we don't block the path. So what does that mean? Let's take a very simple example of a collider path. So we have three variables a, b, c, and a is of course for c and b is of course for c as well. What are the paths? We could go from a to c. This is one very simple path. We could go from b to c. This is another very simple path. But we could also go from a to c and from c against the direction of the arrow to b. Let's practice this again with another example. Let's take the birth weight paradox. The data show the following. If the parents smoke, in particular the mothers, there's a higher risk of a low birth weight and a higher risk of infant mortality. For infants with a low birth weight, infant mortality is lower for children of smoking parents. But this doesn't make sense, does it now? Let's look at the graph. Smoking affects the birth weight. Birth defects also affect the birth weight, and birth weight affects child mortality. Smoking also affects child mortality, and birth defects also affect child mortality. So, what do we do now? We can see that we have a collider in birth weight. Now, if we condition on a collider that we've just talked about, we're looking at infants with low birth weight, or in our previous example, we're only looking at persons who are celebrities in Hollywood and not the general population. We now create a spurious correlation. And that is the danger of all of these variables if you don't understand how they're connected to each other. So lessons learned so far. Correlation still does not imply causation, but the interplay between variables can create spurious correlations even if we don't look at them or if we look at them in particular. Conditioning on a fork will remove the spurious correlation. This was our cholesterol exercise. Right? We look at age groups, but if we condition on a collider, if we look at values from a collider, this was the example we just had with a low birth weight, the collider will introduce spurious correlations. Now, the only way we can disentangle that is to understand the data generating process, and this is something machine learning in general cannot do. The directed acyclic graphs help us to understand the data generating process. As a note, we cannot model the world and include everything and anything. The trick, or if you want the challenge, is to include the right variables in our graph. And of course, we have to know what the right variables are. And this is essentially why you need a lot of domain expertise, because creating many variables and then use feature selections or others will only work by accident because you have this complex interplay between variables, and depending on what you do or don't do, you can introduce spurious correlations. So what can we do so far? We can understand the impact of correlations a bit more. We know that purely data-driven models will, within reason, not work. We know how to create directed acyclic graphs so we can model the relationship between variables and identify that may or may not introduce spurious correlations. What we need is to determine causal effects of doing something, even without actually doing it. This brings us back to our smoking example. We want to establish a causal effect without making young teenagers smoke for decades. And this leads us to intervention and the invention of do calculus. So what are intervention versus conditioning? We've already seen conditioning before when we looked in the cholesterol exercise at age groups. We can rephrase this as seeing versus doing. So conditioning in this sense is seeing. We look at specific part of the data and look at specific values, but we don't change anything. We look at the cholesterol and exercise of the data that we have when we look at specific values. Interventions are then the sort of doing. We actively change our system and observe changes in behavior. If we only had observations, right, we would never see a physician. Because whenever we go to a doctor's office, there's a high probability that we are ill. Right? If we only had observations, we would assume that we would get ill if you go to a doctor. We'd also disband fire brigades, because whenever we call a fire brigade, there's a fire. Right? So we better not call a fire brigade. Of course, this is nonsense. So we need to be able to model interventions. So an intervention is we change the value of a variable, a raise in our DAG, any arrows that point into the variable so that no further influences are there, and we force its value, so we change the DAG in our data generation process. In conditioning, as we only look at specific values of the variables, but the DAG and the model remain the same. And we need to express this mathematically, so we have a new notation, and this is where the do and the do calculus comes in. We say do x equal x, so do set the value of variable x to the value small x. And then we can extend our observation, so we have the conditional probability, for example, to observe the value y for variable y, given that x is x and has the value of x. This is our conditional, and if we do this with the do operator, is that we now observe the probability that the variable y has the value y if we force x to have the value. So there's a subtle but important distinction to make. In the first case, we limit our choice of values we look at, and in the second, we actively change the variable. And then causal analysis generally boils down to that we do something like do make people smoke. But of course, we don't actually want to do this. So we need to reformulate our expressions of do variable x has now the value x into expressions that don't have these do values. So we want to replace our description of interventions with observational data. Right? So as we come back to the example, instead of making the teenagers smoke for decades, we want to look at observational data, because some teenagers will smoke anyway. We need to consider all relevant variables and establish the causal effect. Right? And the caveat is that we need to be really sure that we can prove the causal effect and not some spurious correlation. And this is what the Pearl's do calculus allows us to do. But to do this in full is beyond the scope of this course. Let's take another example, a sprinkler. This has a very simple system. The pavement is very slippery when wet. It may be wet during rain or a sprinkler. So let's model this as a directed acyclic graph with just discrete variables. We have a season, spring, summer, autumn, winter. Our sprinkler can be on or off. We have rain, yes or no. This leads to a wet pavement, yes or no, and the wet pavement leads to a slippery pavement. And as a graph, it looks like this. At the top, we have the season. That affects whether we use the sprinkler or not, because in winter we probably not use it as much as we do in summer. It also affects the rain sprinkler, and rain affects, shall we say, the wetness, and the wetness is the cause of the slipperiness. Also, we know that there is no arrow from season to slippery, because this influence is mediated by the sprinkler, rain, and the wetness. If we know the value of wet, it makes the slippery independent of all others. Like if we know it's wet, it doesn't really matter if it's due to a sprinkler or rain. If it's wet, it will be slippery. We can also say the variable x4, wetness, shields x5 from the rest of the graph. Now let's consider the causal statement. Turning the sprinkler on does not affect the rain. This is true because there is no arrow from sprinkler to rain. We can turn the sprinkler on, it won't make it. Either it won't rain or it won't stop the rain. Whatever we do with the sprinkler doesn't change the weather. You can also now implement a policy. A policy means that we make changes depending on the state of the system. If it rains, turn the sprinkler off. We can do this by adding another arrow, going from rain to sprinkler. Now x3 no longer depends only on x1, the season, but also on x2, the rain. This is a different graph with a different behavior, but we can now introduce such a system and, as we said, introduce a policy. How does an intervention look like? Do x. For example, do x3, the sprinkler on. Or more colloquially, let's switch the sprinkler on. So first, we remove any arrows that go into x3. In our original example, that was just the season, because if we actively switch it on, even if it's pouring outside, the season doesn't have any effect on it. And we set the value of the sprinkler to on because we switch it on. In order to understand the example between conditioning and intervention a bit more, let's consider the following Gaussian distribution. Let's say it's a two-dimensional distribution. You can see the marginal distribution on the two axes, and they are identically distributed random variables. How do we generate these? So the first way to generate this is first generate the x values via a Gaussian distribution, and then the y values by scaling and shifting the x values with another Gaussian. So x is now a causal influence on y, and this leads to the graph on the right. We could also do the following. We first generate y and then does the same for x. Essentially, we flip the role of x and y in the first case. Now y is a causal influence on x. We could also do this in the following way. We first generate z according to the description of a normal or Gaussian distribution, then set the value of x to equal z, and then generate y according to that. Essentially, this is sort of an extended version of our first case where we added the complication of a new variable z. In all three cases, the graph on the right with the distribution and the marginal distribution is exactly the same. But do they also behave the same in the causal structure? Now, if we look at conditioning values, like if we take the conditional, we only look at the distribution of y values for those values where x equals 3. So given what is the distribution of y given we observe x equals 3, and if we do that, all three distributions behave very similar, and you can see that if we sort of slice through this example at x equals 3, we get the following distribution. It's again a Gaussian distribution, and the three of them are the same. Now let's look at interventions. What does it do when we do interventions? Let's look at the first case. Now, instead of observing x equals 3, we set x equal to 3. So we erase any arrows pointing into the variable that is intervened on here, x. Before the intervention, we have x as the cause of y. After the intervention, we didn't have any change because there was no arrow pointing into x. And then at each part of the description, we set x equal to 3. So we generate x equal to a Gaussian distribution, set it to 3. So essentially, we replace the distribution with this fixed value, and then put this into the next line and generate with the Gaussian again, right? So here saying is doing, and there's no difference between observing and doing. In case 2, there is a difference because we flipped the role of x and y. Before we had an arrow pointing from y into x. Now with the do, we remove that arrow, and after the intervention, x and y are uncorrelated. Now let's look at case 3. Again, we remove the arrow, but now the graph is more complicated. We have this common cause x and y. So we erase the arrow into x, and that leaves us with the sort of mutilated graph we see below, and set the value at each part. Right? So the graph now really changes. And what do we do? Our expectation is because seeing is doing, we observe the conditional, and in case 2 and 3, the graph changes, so we observe the marginal. And what you can see, these are not the same. We started from the same generated data, and with different ways we can generate exactly the same data. They behave differently if we do different things to them. So the data generating process matters, and just starting from the data is not enough. What are our take-home messages here? Correlation does not imply causation. DAGs allow us to model the causal relationship between variables and analyze how spurious correlations are introduced. We make the assumption in our analysis explicit and transparent that if we have a specific DAG, we say this is what we know about the system and the data generating process that we want to analyze. Of course, we cannot model the world and include everything and anything, but our DAGs should represent what we want to analyze. It should be as simple as possible, but as complex as necessary. And with the last example, we've seen that purely data-driven approaches do not work, of course with some caveats, right? Because the data generating process is very important and we need to understand how the data come about. So it means we still need experts, at least for now, because causal discovery is a hot topic in machine learning as well. Just to drive this home, the data generating process is very important, and that means also for your practical work, don't just automatically or not generate lots of features, variables, encrypted, whatever, and then use some sort of feature selection heuristic that will work in some cases, but not in others. And in general, it's an unstable approach because you don't really know when it's not going to work. Also be careful with statements like we have established the cause of X is Y, because you probably haven't, and you need to be very careful how you prove this in a mathematically rigorous way. There's also a nice Twitter post which I just put up here. Causal inference comes down to 5 rules. Control for confounders, don't control for colliders. These are the examples with cholesterol and the birth weight paradox we've seen. Control for mediators, the fire or the wet pavement. 4 is important, magically know which stacks to decide. Use random assignments when possible. I use randomized controlled tiles when this is feasible. If you're more interested in getting to know, here is some literature. The Book of Why is a nice popular science book that is the basis also for this presentation, and there are 2 textbooks from Judea, Pearl and others. Causal Inference and Statistics is a short applied textbook which is quite useful, and Causality is then really a more rigorous mathematical one. Of course there are other textbooks like, for example, here from Miguel Hannigan, Causal Inference, but if it's also a free version available for this one.